Good morning, ma'am. My name is N. Vijayaram from CSIT branch. My topic is learning the predictability of the future. Introduction. The future often has no predictability, narrow predictability. Now, no matter how much you study, see in figure 1, you will not be able to anticipate the exact next action with confidence. Go ahead and study. Will they shake hands or high five? One, for the past decade, predicting the future has been a core computer vision problem with a number of applications in robotics, security, and health. Since large amount of videos are available for learning, the temporal structure in unlabeled video provides excellent incidental supervision for learning rich representation. While visual prediction is challenging because it is an unconcentrated problem. A series of results in neuroscience have revealed a biological basis in the brain for how humans anticipate outcomes in the future. However, the central issue in computer vision has been selecting what to predict in the future. The field has, however, central issues in computer vision has been selecting what to predict in the future. The field has investigated a spectrum of options ranging from generating pixels and motions to forecasting activities in the future. However, most representations are not adaptive to the fundamental uncertainties in video. While we cannot forecast the concrete actions in figure 1, nor generate its motion. All hope is not lost. Instead of forecasting whether the people will high five or shake hands, there is something else predictable here. In figure 1, the future of often uncertain. Are they going to shake hands or high five? Instead of answering this question, we should head the bet and predict the hyponym that they will at least greet each other. In this paper, we introduce a hierarchical predictive model of learning what is predictable from unlabeled video. We can hedge the bet and the predict abstraction that they will at least greet each other. This paper introduces a framework for learning the unlabeled video what is predictable. Instead of committing upfront to level of abstractions to predict, our approach learns from data which futures are predictable, motivated by how many people organize action hierarchically. We propose a hierarchical predictive representation. Our approach jointly learns a hierarchy of actions while also learning to anticipate the right level of abstraction. Our method is based on observation that hyperbolic geometry naturally and compactly encloses hierarchical structure. Unlike Euclidean geometry, hyperbolic space can be used as the continuous analog of a tree because tree-like graphs can be embedded in finite dimensions with dimensional distortion. We leverage this property and learn predictable models of hyperbolic space. When the model is confident, it will predict the concrete level of the hierarchy, but when the model is not confident, it learns to automatically select a higher level of abstraction. One to established video databases are results show predictive hyperbolic representations are able to both recognize actions from partial observations as well as forecast hyperbolic representation in future better than baselines. Although our representations is trained with unlabeled video, visualizations also show actions hierarchies automatically emerge in the hyperbolic representations. The visualization also show action hierarchies automatically emerge in the hyperbolic representation. The model explicitly represents uncertainty by trading off the specificity versus the generally of the prediction. The primary contribution of this paper is hierarchical representation for visual prediction. The remainder of this paper describes our approach and experiments. The detailed code and model are publicly available available. Related work. Video representation learning aims to learn strong features for a number of visual video tasks by taking advantage of the temporal structure in video. A line of work uses the future incidental, instead use the natural temporal order of video frames to run self-supervised video representations. While these models learn predictable futures, the underlying representation is not adaptive to the varying levels of uncertainty in natural video. They also focus on action recognition and not action prediction. By representing action hierarchies in hyperbolic space, our model has robust inductive structure for hedging uncertainty. Unlike action recognition, future action prediction and early action prediction are tasks with intrinsic uncertainty caused by the unpredictable of the future. These works are pioneering remaining optimization algorithms are used to optimize the models using hyperbolic geometry. Their success is largely attributed to the advantage of hyperbolic space to represent hierarchical structure. Following the Poincare embedding use a hyperbolic entailment cone to represent the hierarchical relation in a cyclic graph. Since visual data is naturally hierarchical, hyperbolic space provides a stronger inductive bias for the images and videos as well. Performs several image tasks demonstrating the advantage of hyperbolic embedded over cross model to perform hierarchical action search. We instead use hyperbolic embedding for prediction and we use a hierarchy to model uncertainty in future. Mm. A high covariance indicates that the model is confident about its prediction and exposure variations. These models allow sampling from the latent space to capture the multiple outcomes in output space. Probabilistic approach are compatible with our framework. The main novelty of our method is that we represent the future uncertainty hierarchically in a hyperbolic space. The hierarchy naturally emerges during the process of learning the predict the future method. We present our approach for hierarchical representation of the future. We first discuss our model, take and introduce our hyperbolic representation. Hierarchical representation, the key contribution of this paper is to predict a hierarchical representation of the future. When the future is certain, our model should predict as specifically as possible. However, when the future is uncertain, our model should hedge the bet and forecast a hierarchical parent. This density allows hierarchies and trees to be compactly embedded. Classification. After the represent of Z is trained, we are able to fit any classifier on top of it. We usually we use a linear classifier and keep the rest of representation fixed. However, since the representation is hyperbolic, we cannot use standard Euclid linear for the Euclidean baseline. We train a standard Euclid multi-class logistic regression in both models. We treat each node as independent category. Network architecture. While we estimate our prediction and loss in hyperbolic space, the entire model does not need to be hyperbolic. The flexibility enables us to take advantage of the extensive legacy of existing neural network architectures and optimization algorithms that have been highly tuned for Euclidean space. And this is precisely the connection between the two spaces. We use an exponential map entered at 0 to project from the Euclidean space to the hyperbolic space. When the representations are in the hyperbolic space, the mathematical operations and optimization follow the rules derived by the metric in that space. Experiment. The basic objective of all our experiments is to analyze how hyperbolic representations encode varying levels of uncertainty in the future. We quantitatively evaluate on two different tasks and two different data sets. We also show several visualizations and diagnostic analysis. This is the diagram data sets and common setup. We use a common evolution setup throughout our experiment. We first learn a self-supervised representation from a large collection of unlabeled videos by optimizing and fine gym is a data sets of gymnastic videos where clips are annotated with three-level hierarchical action labels. Movies in our second sitting, we learn the self-supervised representation of MovieNet, then fine-tune and evaluate the Hollywood datasets. MovieNet contains movies and keyframes in order to obtain a hierarchy of actions from Hollywood at the video level. We grouped action classes into more general one to form a two-level hierarchy. The hierarchy is shown in supplementary materials since Hollywood does not have evaluation metrics is our quantitative evaluation. Our goal is first we want to evaluate that and obtain representations. Accuracy is standard classification accuracy compares only classes at the lowest hierarchical level. Bottom up hierarchical accuracy is a prediction considered partially correct if it predicts the wrong node at the leaf level. Top-down hierarchical accuracy is in the hierarchical metrics literature. It is sometimes argued and predicting the root node correctly is more important than predicting the exact leaf node. Early action recognition, we first evaluate on the early action recognition task, which aims to classify action that have started as indicated by both hierarchical accuracy metrics. When there is uncertainty, the hyperbolic representation will predict a more appropriate parent than Euclidean representation. Conclusion: while there is uncertainty in the future parts of its predictable, we have we have introduced a hyperbolic model of video prediction that represents a uncertainty hierarchical. After learning from unlabeled video, experiments and visualization show that a hierarchy automatically emerges in the representation, encoding the predictability of the future. Thank you.